All right, this ought to be a quick one. It's a motivation for what you're going to read in chapter 3 about Thomas Fermi-Dirac theory. In the end, what happens there is they write out for you the simplest density functional theory, the earliest density functional theory. And it's one we don't use anymore. It's just not accurate enough. But the ideas behind it are the key. And so that's what I want to highlight in somewhat different forms here. What's the idea of density functional theory? It is to get rid of h psi equals e psi. I want the energies. We rarely, if ever, use the whole wave function. We use the density a lot, but we don't use the wave function all that much. So, we're going through a lot of work, and I'll try and exemplify that to solve for psi in order to get e. And you want to replace it with something that just says, well, if density is important, is the density something that determines e? So why would you want to do that? Let's look at four systems and ask, what's the work involved in solving the Schrodinger equation? So here's the hydrogen atom. And the Schrodinger equation, we don't write it down, h psi equals e psi. And if we write it in atomic units, and that's something I haven't talked about much here, I think most of you have seen it before, but it was a very clever set of units that were devised that said, look, why carry around minus h bar squared over 2m? Why carry around e squared over 4 pi epsilon naught? Let's set all the constants, the fundamental constants, to 1. And it's easy to write down that Schrodinger equation because the m goes away and the h bar squared, and e squared of 4 pi epsilon naught. And the units now become Hartrees that are natural sized units for atomic systems. The energy of hydrogen is minus 0.5 at atomic units. So in any event, the solution for this is just a single spatial orbital times a spin orbital. That's easy enough. Now I'm going to do neon. So now my Hamiltonian has, 10 kinetic energy terms and 10 attractions to the nucleus. And, I forgot about the 10 times 9, 90 divided by 2, 45 repulsions. What was I thinking here? A whole bunch of electron repulsions there. And the simplest wave function we could write down for that will have a Slater determinant of 10 spin orbitals. There'll be an orbital for each electron, and that's the simplest wave function. Now you go up to DNA. There will be tens of thousands of coordinates solving for psi sigma I, the state you're interested in, and all you want out is the energy. Almost all the information in that wave function is thrown away. And then if you think about a solid, and that's initially what physicists were interested in when they were thinking about density functional theory. Look, slab of solid has Avogadro's number of particles. I can't have a function that has Avogadro's number of coordinates. That's impossible to work with. And so getting the energy out seemed impossible. Now, what you need to remember is the relationship between the wave function and the density would determine most one electron properties, so like dipole moments and quadrupole moments, things like that. And also the charge distribution, which you can measure experimentally doing X-ray crystallography. The density looks like this. Take the absolute value of the wave function squared. You integrate out all the positions of all particles but one and all the spins. That is the, and you multiply by n, which is the number of particles. That's the density. The beautiful thing about the density is, no matter what the system, it only depends on 3 coordinates. So for hydrogen, here's what it looks like. You absolute value square the wave function after having integrated out spin, that's the density, depends on 3 coordinates. The density for neon, calculated as we would above, is 2 times the density of electrons in the 1s, 2 times the 2s, 2 times each of the 2 p's. It's going to add up to 10 electrons, 3 coordinates. And DNA only depends on 3 coordinates. So if it were the case that there was a relationship that uniquely defined the energy, if I knew the density, our lives would be simpler. We would solve for this function, 3 coordinates, no matter what the system, and we would get the energy. Now, at the time of Thomas Fermi-Dirac theory, that was plausible. Because what they knew is, density had to integrate out to the number of electrons, so it told me the right number of electrons. They knew that row of R has cusps, the nucleus. So it told you where the nuclei were. And they also knew that the cusp shape of the nucleus was related to the actual nuclear charge. So you didn't just know where the nuclei were, you knew what their charges were. And so Thomas and Fermi wrote down this really simple theory. So let's just look at the pieces. This right here is just the electron density attracted to each of the nuclei. This is the uncorrelated self-interaction contaminated electron-electron repulsion. It's a charge density repelling itself, but it's certainly related to an electron repulsion. This piece up here is the kinetic energy, and so that's why I subscripted the constant in front of it, KE. You take rho to the 5/3 at a given point, multiply by the little volume element, you add them all up. And that was the initial estimate of the kinetic energy. But you only need rho, but the problem is there's no exchange, there's self-interaction, there's no correlations. The first fix actually came in the form of an exchange term that now looks like rho to the 4/3. And this could be negative, but you take the density to the 4/3 power in interval space, multiply by a constant, and it estimates the exchange interaction. And it's really for a uniform electron gas, which we'll see in a little bit. This was used for a long time to study solids. It's terrible for molecules, due mostly to the fact that the kinetic energy part is horrific. It's bad. But the question that people asked and continue to ask, although it was used, is this justified at all? This was all predicated on the thought that there was a unique relationship that given rho, I could get the ground state energy. Is that justified? And if it is justified, well, this is still pretty terrible for molecules. Can we improve on Thomas Fermi Dirac theory? And that is chapter 4 and 5.